Now the last part of this model is Routh Stability Criterion or Rouths Hurwits Criterion. Now let us consider a simple example of a closed loop transfer function to find its stability. So this is a given equation that is 10 divided by s plus 2 into s plus 4. So we are interested in the system output. So I'll rearrange the equation C of s is equal to 1 by s because the step input that we are applying multiplied by s plus 2 and s plus 4. By using partial fraction we can solve this problem, or we can get back C of t, that is the output response in time domain. Now before we go to that, let us observe the roots of this system or the poles of the system. So one we have s is equal to 0, other we have s is equal to minus 2, and the other one is s is equal to minus 4. As you can observe the s domain, one pole is at the origin, the other two poles are at the left side of the system. The moment you see the poles exist at the left side of the system, you can directly say that the system is stable. Now, how do we know that the system is stable? If you observe the output C of t of this control system, the 1.25 is steady state value, 2.5 e power minus 2t plus 1.25 e power minus 4t is the transient state. Now I want the transient to diode. If the transient exists for till even infinity, then the system is said to be unstable. Now in our case it is e power minus 2t. If I vary the time with respect to infinity, since it is negative decay, the exponential term will diode at infinity. Again in the second term I have 1.25 e power minus 40. Again this whole term will diode because it's exponential decay, negative term. Now when I compare these two equations, which term will diode fast? E power minus 40 will diode fast compared to e power minus 2t. That means if I have a pole placed towards left side, then it is more stable compared to this, that is e power minus 2t. Now we take the second example, that is 10 divided by s minus 2 into s plus 4. Again if I rearrange the equation, I get 10 divided by s into s minus 2 s plus 4. In this case the poles are s is equal to 0, s is equal to 2 and s is equal to minus 4. As you can observe, one pole is at the right side of the system, and when I see the equation, that is C of t, I know that C of t is equal to minus 1.25 plus 0.833 e power plus 2t plus 0.416 e power minus 4t. So one term is negative decay, negative exponential decay, whereas the other term is exponential rise. That means at the point of infinity I get an infinite value. If I have a system, if I have an output response in this type, then the system is unstable. So as you can see, if any one pole exists at the right side, then I can easily say that the system is unstable. Even though in the system there are terms which is negative or which is at the left side, still the system is unstable. So as I increase the value of t to infinity, the final value I get is infinity. This is because of this one term, that is 0.833 e power plus 2t. Now what do we understand from this? We understand that if any poles exist at the right side, then the system is unstable. If any poles exist towards the left side, then the system is stable. Other than this, there are two more terms. If there is a repeated roots, then the system is unstable towards the left side. If there are non-repeated roots, then it is marginally stable. So for stable condition, there are only two things. One is the pole should exist towards the left half of the S plane. The other is it should be non-repeated roots. For unstable, there are two conditions. If the poles are at the right side of the S plane and if there are repeated roots, then we can say that it is unstable. So the concept of stability, a stable system is a dynamic system with a bounded response to a bounded input. Consider closed loop transfer function of a system. T of s is equal to bm s to the power of m, bm minus 1 s to the power of m minus 1 till b naught, a n s to the power of n, a n minus 1 s to the power of n minus 1 till a naught. So I represent the numerator as n of s and denominator as delta of s, which is a characteristic equation. So characteristic equation is nothing but a n s to the power of n plus a n minus 1 s to the power of n minus 1 till a naught. For the system described by a transfer function to be stable, the roots of the characteristic equation must lie in the left half plane. This is a very important sentence. Now, the Rouths Hurwits criteria or test is a numerical procedure for determining the number of right half plane and imaginary axis roots of the characteristic polynomial. Now, Rouths Hurwits method stability criteria. Step 1. Generate a data table called Routh table as follows. For example, if the equation is given like this, depending on the order. So, first one is S4, S3, S2, S1, S0. We write it in a column wise basis. And the coefficients of the power we alternately we write. So, for example, the first one is A4, we skip A3, we go with the second order, that is A2. Then again we skip A1, we write A0. So, it is A4, A2, A0. The next one is in the power of S cube, we write the coefficient A3, then we go with A1, next the value, there are no other values, so it is 0. So, it is A3, A1, 0. So, any row of the Routh table can be multiplied by a positive constant without changing the values of the rows below. To avoid the division by 0, an epsilon is assigned to replace the 0 in the first case. Epsilon is a special case, we will go to it in the next slide. Now, how do we solve this? So, first thing is we consider we multiply A3 multiplied by A2, then we take a minus sign, we consider A4 multiplied with A1, we divide it by A3. This value is nothing but B1, that is the determinant of A4, A3, A1 and A2 divided by A3 is nothing but we get B1. For the next value, again we do the same thing, we multiply A3 multiplied by A0, again negative sign, A4 multiplied by 0 divided by, again we consider the same parameter, that is A3. So, we get B2. Similarly, for this we take A3 multiplied by 0, A4 multiplied by 0 divided by A3. Now, in the s to the power of 1, we should get C1. How do we get this? So, what we do is we take B1 multiplied by A1, again A3 multiplied by B2 divided by B1. We get the value C1. Similarly, for this, the next case, it is B1 multiplied by 0, next A3 multiplied by 0 divided by B1, we get the answer as for C2. Similarly, it goes on. Step 2. Interpret the Routh table to tell how many closed loop system poles are there in the left half plane and in the right half plane. Like if in the values of the first column, if there are positive sign, we say that it is at the left half plane. If we have negative sign or change in sign, then it is at the right half plane or unstable plane. If the quotient of the characteristic equations have differing algebraic, then there is at least one RHF, RHP roots. For example, the moment you see the equation, there is negative sign here. It indicates that one or the two roots are at the RHS, that is the right hand side of the plane, or RHP. If one or more of the coefficients of the characteristic equations have zero value, there are imaginary or RHP roots or both. That means it is s to the power of 6, 3s to the power of 5, 2s to the power of 4, but there is no cube which is left out. If you find such an equation, then it is directly known that there is one zero value, or there are imaginary or RHP roots, or both in a system. Now let us consider an example. So this is a feedback closed loop system given. For this we need to find if the system is stable or not. So first we'll find the total transfer function of the system. Since it's a minor feedback loop, so it is g of s divided by 1 plus g of s into h of s. So I can easily find the transfer function. So in this it is 1000 divided by s cube plus 10s square plus 31s plus 1030, and this is the characteristic equation. And as you can see, all are positive. It indicates that the system might be stable or may be unstable. So we'll use Routh's criteria. So first thing, we write down all the powers. So highest power is s cube, s square, s to the power of 1 and s to the power of 0. Now the coefficient of s cube is 1. So we skip the second term. We'll go with 31. We'll skip the next term and we'll go with the other term is nothing but 0. So we consider 0 and 31. For s square, we start with 10s square, so it is 10. The next value we'll skip this, so we'll go with 1030. So we go along with this, and the next term is 0. So we now we'll since we need some constant value, we can easily divide this to reduce the complexity, or you can directly multiply as it is. Both will give the same value. There is no change in the value. So since we have divided by 10, I can write this as 1. Here we can write it as 103. Now the first solution. So we multiply 1 with 31. Then we subtract 1 into 103. So 1 into 31 is 31 minus 103 divided by the same term. So it is 1. So I get answer as minus 72. Again the next value, what we do is 1 multiplied by 0, we get answer as 0. Again 1 multiplied by 0, the answer is 0. So the whole thing is nothing but 0, and it goes on. So in this S naught part, I got the answer as 103. That is nothing but minus 72 into 103 minus 1 into 0. So 72 into 103, I get a positive negative value, divided by minus 72 means we get a positive value. So it is 103. So there are two sign changes. What you need to observe is this is plus, plus, I have a minus sign, again I have a plus sign. So plus to plus there is no sign change, again plus to minus there is one sign change, again from minus to plus there is two sign change in total. Hence the system is unstable. Now we'll take another example. In this case we have 10 divided by 3s to the power of 5, 5s to the power of 4, 6s cube, 3s square, 2s and 1. So we'll write, first we'll write all the powers, s to the power of 5, 4, 3, 2, 1, 0. Next we'll write the coefficients of s to the power of 5, so which is 3. We'll skip 5s to the power of 4, the other one is 6. and we'll skip 3s square, so it is 2. The next value is 0. We don't no need to consider. Now s to the power of 4 is nothing but 5, that we consider this value, and it is 0. And in the other case we consider this, we consider this part and this part and this part. So it is 5, 3 and 1. And when I solve the first part, that is 5 into 6, 6 5 is the 30, minus 3 into 3 is 9. So 30 minus 9, we have 21. 21 divided by 5, we get answer as 4.2. Similarly, we multiply 5 into 2 minus 3 into 1 divided by 5. So we get answer as 1.4, and we continue this. Now as you observe, the first sign is plus, positive, positive, positive. Until this point, all the roots are at the left side, so the system is stable. But at s to the power of 1, I got one negative sign. Again there is positive sign, so it is plus to minus, again minus to plus. Since there are two RHP roots, the system is unstable. If you find all the signs of the first column as positive, then the system is stable. The next example is determine the range of values of k. Now from this what we can understand is, if I add again a constant k to the open loop system, I can move the system condition from unstability to the stable condition. So I can write this C of s divided by R of s as k into g of s divided by 1 plus k into g of s into h of s. Now in this, the characteristic equation is 1 plus k into g of s into h of s is equal to 0. The location of the roots of the above equations are dependent on the proper selection of values of k. Hence, such a system where stability depends on the condition of parameter k is called as conditionally stable system. Now let us consider an example where a characteristic equation of a total transfer function is given, and we have s to the power of 5 plus 13 s to the power of 4 plus 54 s cube plus 82 s square plus 60 plus k into s to the power of 1 plus 3k to the s to the power of 0. Now we will solve this by Routh Hurwits method. So first we will write all the powers starting from s to the power of 5 in a column wise, reaching s to the power of 0. Next we will write the first coefficient of s to the power of 5. Next we have 54. Next it is 60 plus k. Next the value is 0. So it is 1, 54, 60 plus k. In the next row, we consider 13, 82 and 3. After that, the value is 0. So it is 13, 82, 3k. Next, how do we solve? We multiply 13 into 54 minus 1 into 82 divided by 13. We get the answer as 47.7. In the next case, we take 13 into 60 plus k minus 1 into 3k divided by 13. We get the answer as 60 plus 0.769 k, and we continue as it is. Now for the system to be stable, the first condition is all the first column should have a positive sign. Now to know the limits of k under which the system is stable, I know that this s to the power of 0 value, the first column value 3k should be positive. When it will be positive? When the k is greater than 0. So this is the first minimum limit, that is k should be equal to 0. To find the limit of second, we can see that here for this condition should be greater than 0, that is 65.6 minus 0.212k should be greater than 0. Then the k value we get is 309. So the upper limit to this system is k should be less than 309. Now let us test this for the second equation. So in the second equation we have 3940 minus 105k minus 0.163k square should be always greater than 0. So k square, that means there are two k values. Okay. So in that we get one k value as 35. So because when I substitute the k value here 309, I get the k value, the final resultant value as 35. So the range of k where the system becomes stable is from 0 to 35. Now let us consider a special case in which let us assume that when you are solving the Rouths array, one of the row becomes 0. Then what to do? We cannot consider that the system is unstable. We need to modify the system in such a way that the system we should be able to solve the problem. So in this example we have s to the power of 5 plus 2s to the power of 4, 3s cube, 6s square, 5s plus 3. So again I arranged all the powers in this order. Next, s to the power of 5 is coefficient is 1. We go with the next value is 3. Next value is 5. So it is 1, 3, 5. In the next row, we go with 2, 6, 3. So it is 2, 6, 3. And as you can see, 2 into 3 is 6. 1 into 6 is a minus sign. So 6 minus 6 is 0. 0 by 2 is nothing but 0. So we got this problem. Now what we need to do is when we have such condition, we need to replace the 0 by a positive sign epsilon. Then we are able to continue this uh, problem. So it is again epsilon. So it is epsilon into 6, 2 into 7 by 2 divided by epsilon. We get an equation further, that is 6 epsilon minus 7 divided by epsilon. Again we get further equation and we can solve till s to the power of 0. Understand this, to solve Routh's array we need to solve until s to the power of 0 and we should get some positive values. We may get a negative value but there should be some real values. Now, how do we find the system is stable or not? We have assumed that the epsilon value is positive value. Again, in this case, 6 epsilon minus 7 divided by epsilon. Let us assume, let us say, take limit epsilon tends to 0. Now, what will happen? I get a negative sign, that is minus 7. Why? Because it is 6 epsilon minus 7 divided by epsilon. So epsilon gets cancelled, so I am left with 6 minus 7 divided by epsilon. That is nothing but 6 minus epsilon. If epsilon is 0, it is 7 by 0, which is infinity. So 6 minus infinity, I get some minus infinity. So at this point I get a sign minus infinity. So since I got minus infinity, it indicates that the system is unstable. So I have plus sign, plus sign. Here we have assumed that epsilon is positive, but in the next case I am getting a negative infinity. Again, in this case I may get a positive sign or negative sign. Anyhow, the system has become unstable. So positive Interpret the Routh table to tell you how many closed loop system poles are in the right half plane. To begin the interpretation, we must assume a sign positive or negative for quantitative epsilon as illustrated in Routh's table. Now we consider case 2. In case 2, let us assume that the whole row has become 0 when we are solving this. Then what to do? Then we can take an auxiliary equation. How we are considering this auxiliary equation? We consider the previous value and the powers. So this is nothing but s to the power of 4, and we'll skip s cube. Then we take what? S square. Then we skip s to the power of 1. Then we take s to the power of 0. So I can write this as 3s to the power of 4 minus 48, because this term is 0. There is no need to consider. Now again, if I differentiate this, I get 4 into 3, which is nothing but 12. S to the power of 4 is nothing but s cube. So we consider 12 s cube. So to solve this, we have 1, 3, minus 16, minus 48, 4, 0, minus 64, 0. From the previous equation, auxiliary equation, we got 3, 0, minus 48. From auxiliary equation solution, we got 12, 0, 0 and 0. Again, when we solve, there is a term 0. Then we can use the special case 1, that is we substitute positive epsilon. So when we substitute positive epsilon, we get the answer plus 576 divided by epsilon 0, again 0, and the final value we get is minus 48. So when we see is the system is stable or not, it depends on the auxiliary equation. Since we have considered the auxiliary equation, we need to find its root. Just by seeing the first column, we cannot say that the system is stable or not. By observing the roots of the characteristic equation, we can say that the system is stable or not. So the roots that we get are plus 2, plus or minus 2j. Then we have the other three roots. So we can say there are totally 6 roots, because s to the power of 6 is the function. So we have plus and minus 2 real roots, and we have 2 imaginary or the complex roots, but both are not repeated roots. Since they are not repeated roots, so the system is in the direction of stable. The next part is marginal k and frequency of sustained oscillation. Marginal k values is that value of k for which the system becomes marginally stable. For marginally stable system, there must be a row of 0 occurring. So the value of k which makes any row of the Rouths array or the row of zeros is called marginal value of k. And marginal value of k is a value which makes any row other than s to the power of 0 as row of zeros. This is a very important sentence. To obtain the frequency of oscillation, solve the auxiliary equation a of s, which is equal to 0 for k equals k marginal. For a of s is equal to 0 at marginal value of k indicates that the frequency of sustained oscillations. So we take an example. G of s is equal to k divided by s plus 2, s plus 4, s square plus 2s plus 25. So from these two terms, we can say that the system is stable, because we are getting poles as minus 2 and minus 4. But when we take this quadratic equation s square plus 6s plus 25, we are not able to say the system is stable or not by finding the roots. And as we know, since there is a k value, the k is able to make the system from instability to stability depending on the ranges of the k value. So first we rearrange the system. So the first we will find the characteristic equation. So it is 1 plus g of s into h of s. So it is 1 plus k divided by s plus 2 s plus 4 s square plus 6s plus 25. And since it's a unity feedback, h of s is equal to 1. So when I solve this equation, we get uh, the first s to the power of 0. We got equation as 200 plus k. So first thing is, the 200 plus k should be greater than 0 for system to be stable or to be positive. So k initial condition range is k is should be greater than minus 200. The next case is, from this equation I can easily find, it is 7995 minus 12k. This should be greater than 0 for positive values, for system to be positive. So the k value that I get is 666.25. So the k lies between minus 200 to 66.25. And what is the marginal value? The marginal value is this, that is 666.25. So for k marginal value 666.25, I can find the auxiliary equation, that is 52.5 s square plus 200 plus k is equal to 0. So if I solve for s square, I get the equation as s is equal to plus or minus j 4.062. As you can see, if there is a non-repeated complex number, then it is a marginally stable system. So this is a one example of such system. And from where we got the auxiliary equation, we need to consider when the row is becoming 0. The previous row of 0 is nothing but the auxiliary equation.